Buck converters. They're a type of DC-DC converter that converts a higher voltage to a lower voltage. In this video, I'm going to be going over some of the basic operational concepts. We're going to be doing some circuit analysis, and we're going to be looking at some waveforms for the buck converter. But before I get into any of that, please be sure to like and subscribe. That helps my channel out a ton. I would really appreciate that. And also throughout the video, if you have any questions or comments, then drop a comment down below. I'd be happy to answer it, and I'll even make separate videos if you need some clarification on something. So with all of that out of the way, let us just jump right into it. Oh, also, stick around to the very end because I'm going to be going over a variant of the buck converter, and I'll be talking about that a little bit. So that's going to be at the very end of the video. So make sure you watch the whole thing all the way through. So the buck converter, right? What I've done right here is just taken this little diagram right here. It says the schematic of a non-synchronous buck converter. So this is like your basic schematic in terms of it shows all of our fundamental circuit elements. And then we can talk about the mechanisms of action for it. So I just went ahead and labeled all of the components of interest here. So we have the MOSFET, which is Q1 right here. We have the inductor, which is L1 right here. Then we have the input capacitor, which is Ci, the output capacitor, which is Co, and then we have the diode D1. I went ahead and added a couple elements to this circuit. So this is a diagram I pulled off the internet. And then I went and added this little voltage source right here, and then I added a load resistor or a load resistance just to represent our load right here. And I think this will help clarify things when we get into our explanations. So these are all the main circuit pieces that are involved in the buck converter. Like I mentioned, the buck converter, the idea is this is going to be like a 24 volt source, and then we can drop it down. The voltage across the load right here could be something like 5 volts, 3.3 volts, whatever you want it to be. So the key concept for understanding how this thing works is it's based entirely on the inductor right here. This is all these elements are working to let this inductor do its inductor thing, basically. So if you know anything about inductors, we know that inductors like to maintain a constant current through them. So here I have drawn on the circuit schematic, we have I sub L1. So this is supposed to denote the current that's flowing through the inductor, and that's going to be flowing across the load. So like I said, they like to maintain a constant current through them. So once we get the current up to a certain value, and then say you just pull the plug on it, it's going to try to maintain that constant current in the rest of the circuit. So they will resist any changes in current, either increasing or decreasing, and we'll get to that in a second, because basically there'll be two instances, two sort of conditions for the circuit that we'll talk about, where the inductor will be resisting an increase in current, and it'll be also resisting a decrease in current as well. So the first condition that I want to talk about here is the condition in which the switch is closed. So this little green box I have drawn here on the circuit is going to represent the flow of current when the switch is closed. So we're starting here at our voltage source. The switch is closed, so current is allowed to flow through our MOSFET, and then it's not allowed to flow down this way because we have our rectifier diode is prohibiting current from flowing that way, right? Because eventually we know we're trying to get back here to create a return path. So we're going to go through our inductor, and then we're going to go across our load, and then we're going to just loop all the way back down to complete the circuit at the negative terminal of our battery. So this is the condition. Like I said, this is when the switch is closed, and then during this condition here we have the current through the inductor ramps up linearly, because remember how I said an inductor likes to resist a change in current. So before the switch was closed, there was zero current flowing through this inductor, so it's going to resist it. So that's what gives us that linear ramping, and I'll show you a graph here in a second, but it looks just like a linear straight line heading up as current slowly increases through this inductor. And this is the phase where if you look up any tutorials on YouTube besides mine, or look up on the internet, they'll refer to this as the inductor is quote unquote charging at this time. So basically there's energy being stored in the inductor that is later going to release during the second condition. But first, before we talk about the second condition, let's just look at the graph. So this is kind of what I was talking about is T1 is when the switch is closed. So pay attention to T1. So this is a graph of the current through the inductor. So like I said, the current is slowly ramping up. And then this is also right here, this is a graph of current through Q1. So it kind of lines up, it makes perfect sense. So when the switch is closed, this is T1, T1, T1. Then we have current is ramping up as well because current is allowed to flow through our Q1 and through our inductor. And then through the diode, we said no current is flowing through here because if you look, and that matches up perfectly with what this little green box says, because the green box says there's no current flowing through the diode at all. So again, this is only pay attention to T1 in all of these graphs, and we'll talk about T2 next. But hopefully this makes perfect sense to you where, like I said, we're slowly ramping up current, and then the current across the load is also going to be doing the same thing that the current across the inductor is. And this makes sense as well because all these elements are in series, so we know that the current through them will look all the same. Okay, so next up we're going to be talking about the other condition, which is when the switch is open. So when the switch is open, then what happens is the current through the inductor starts to ramp down, right? Remember we said current, the inductor is trying to resist a change in current. So here we have the current ramping up to a certain value, and then we pull the plug on it, and the inductor's like, no, 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 I don't want to change. This isn't a phase, you know, I'm not going to change. And so it's trying to maintain this level of current, but obviously it can't. It's trying as hard as it can, but it can't do it. So then it's going to start to slowly reduce over time. But what happens is, since there's like basically what's happening is the inductor is now like our current source, our voltage source. So what's going to happen is current's going to flow through the inductor across our load again. But then this time it's going to go through the diode because we need to complete the circuit here. So, and with an open MOSFET, it cannot flow through this back half of the circuit, if that makes sense, right? Because this is treat this as an open circuit right here. So it has to flow through the diode to complete the circuit. So that's kind of where the diode comes in as well. So looking at the waveforms again, and here quickly, if you look up on the internet, they'll say this is the phase, this is the condition or the part of the behavior of the circuit where the inductor is discharging. So like I said, the current through the inductor ramps down, which matches perfectly with the graphs that we're looking at right here. So we're looking at T2 is when the switch is open. So this is the current through the inductor. It's going to slowly ramp down. And then we have current through Q1 is 0, right? Because we open the switch, so nothing. And then that makes perfect sense with the graph that we have drawn right here. No current is flowing through the MOSFET at this time. And then we have current through the diode. And then again, this also makes perfect sense because so the diode's in series now with the inductor. So we're going to see the behavior of the ramping down portion. And then it's going to go from a point of 0 current, right? Because in this section, there was no current, and now we have all of the current that is slowly decreasing. So hopefully that makes a lot of sense to you about kind of what's going on here. So the idea is, like, again, we're taking advantage of the natural attribute of inductors that they like to resist a change in current, right? So that's kind of what the idea is here. So the final comments I kind of want to make regarding understanding how this works is, so we have the input and output capacitors. Their job is for smoothing purposes. So if you kind of look at this waveform through the inductor, so the waveform through the inductor is going to also be an exact match to what the current through our load looks like, right? And so we don't, and we're trying to create a DC source, a direct current source, a very smooth, flat DC line, not some jagged triangle wave. Like electronics can't really work that well with this. So we use smoothing capacitors. So the input and output capacitors are there for smoothing purposes. So they're going to take this triangle wave and try to smooth it out to be as flat of a line as possible. And then the next thing, what kind of tripped me up when I first started learning about this is understanding what the purposes of the diode are. So the diode's job is to direct the flow of current in the two conditions described above. When the switch is closed, the diode is preventing the current from circumventing the load because, so let us imagine when the switch is closed, if this was just replaced with a wire, right, then the current would just totally circumvent, remember path of least resistance, it's totally just going to circumvent this entire portion of the circuit and just go, yeah, no, I'm not going to do that, and then it's just going to go around like this, right, if the diode wasn't there. Okay, now during the switch's open condition, the diode is closing the circuit so that the inductor can properly discharge. So we need the inductor to be able to properly discharge, and in order to do that, we need some kind of connection from this terminal of the inductor and ground, and so that's where the diode comes in handy. It's like a one-way street, allowing the inductor to have its circuit path closed whenever we need it to, and then preventing the circumvention from the rest of our circuit whenever the switch is closed, right? So I hope that makes perfect sense of kind of like what's going on and kind of how the whole thing works. It's extremely simple, right? Especially if you go back, if you watch my flyback converter video, this is a lot simpler. So yeah, this should be a cakewalk if you watch the rest of my videos, I think. So lastly, what I want to talk about is what I mentioned in the beginning of the video is there is another way to design a buck converter, and it is known as the synchronous buck converter. So if you look up at the top, it says schematic of a non-synchronous or asynchronous buck converter. Then this one says a schematic of a synchronous buck converter. So what they have done is basically replaced the diode with a MOSFET. So basically you can open and close this circuit right here at will whenever you want to, and basically it does the same exact job as the diode. If I can explain that as clearly as possible, like it's literally doing the same thing where it's allowing the circuit to be closed during this phase of operation, and then it's causing the circuit to be open during this phase of operation, right? So basically whenever this MOSFET is closed, this one's open. Whenever this MOSFET's open, this one's closed, right? So they're just kind of toggling on and off, and they're going to be opposites of each other at all times. And so the reasons we might want to use a synchronous buck converter over a non-synchronous buck converter is due to the forward voltage drop of the diode. As you know, the diodes have a forward voltage drop, and so they dissipate a lot of power and they generate a lot of heat, right? So depending on some of the external constraints on your project, you might opt for a MOSFET because for one, it could be more efficient, and then two, it could generate a little bit less heat depending on some other constraints on your circuit. But the main advantages of the non-synchronous or asynchronous buck converter are that it's much simpler to create, and it's much simpler to design, right? And then it's much cheaper. Well, not much cheaper. It's a little bit cheaper than a synchronous buck converter, because the synchronous buck converter, you have to also, another MOSFET is a little more expensive than a diode. So basically you have the trade-off between simplicity and BOM cost and efficiency, right? So at higher power requirements, it may be beneficial to swap the diode for another MOSFET. So that's kind of the notes I have there. So that's pretty much everything I wanted to cover in this video regarding buck converters. If you have any questions, go ahead and drop a comment down below. I'll be happy to answer them. And if it's a big, massive question, I'll just make another video to explain stuff. So thank you so much for making it to the end of the video, and hopefully I will see you in the next one.